So we're going to be looking at the study guide for Chapter 2 for the upcoming geometry test. This is on proofs and logic, and so let's get started. The first one is about finishing a pattern and then writing conjecture. So just remember, the word conjecture simply means your description of what's happening or what you think will happen next or what you think the rule of the situation is. So the first one here, we want to first finish the pattern and then we'll figure out what the rule was, because usually in finishing the pattern, you would develop your own conjecture. So we go 4 to 9, and then 9 to 14, and 14 to 19. So let's see what's happening here. Well, 4 to 9, the easiest thing to do would be plus 5. There's a few things you could do, but let's start with the easy one. 9 to 14 was also plus 5. So we can be pretty sure of ourselves right now, but let's just double check. 14 to 19, well, that's plus 5 too. So we can pretty much assume that the next one's going to be plus 5, which is going to give us 24, and plus 5, which would give us 29. And then our conjecture would simply be add 5 to the previous value. So that one's a pretty straightforward one. Again, we finished the pattern, and then from the pattern, we're able to state our conjecture in our own words. And then this is a version of inductive reasoning because we're using past examples to predict what's going to happen in future examples. The next one's not as straightforward, so let's see it. So there. Let's see what's going on. So 75 to 73, well, the easiest way to do that would be minus 2. 73 to 69, well, that'd be minus 4. 69 to 61, that'd be minus 8. 61 to 45, that'd be minus 16. So we can probably see what's happening now. In this case, it's probably going to be the fact that we're subtracting twice as much each time. So we'll go minus 2, then minus 4, then minus 8, then minus 16. So the next one is probably going to be minus 32. And the one after that would be minus 64. So we think about that real quick. 45 minus 32 is going to give me 13. 13 minus 64 is going to give me negative 51. And our conjecture would simply be subtract twice as much as you did before. Now, these conjectures are stated in your own words, so the language doesn't have to be so technical. You can kind of use your own wording there as long as you get the point across. In this case, subtract twice as much as you did before is perfectly fine language. So that's the conjecture and pattern bit. Again, I would recommend you finish the pattern first, and then from that, you'll probably have your conjecture already formed in your mind, and you can just write it out. The next ones are about converting stuff into conditional. Now remember, a conditional is an if-then statement, and there's two ways of going about this. First is to think of it as a cause and effect. So when you read the problem, think about what is the causal part and what is the effect that gets resulted from that. The other thing is that if you see the word is usually a pretty good indicator about the split between if and then. So is the point where the if statement stops and the then statement begins. So like in our first one here, we see that we have the word is right here. The product of two negative numbers is a positive value. So that means that this part is probably going to be my if, and this part is probably going to be my then. So the way I would format this, the product of two negative numbers. What does product mean to do? Well, it means multiply. So I would say if you multiply two negative numbers is, which is our start of then, so comma, then, and it says positive value, which they're talking about the result, right? So then the product, or you can say the result if you don't want to use the word product, is positive. Positive. So one way is if you have the word, you can use the word is to guide your split there. Now there are different versions of this conditional you could draw from this, but this would be the most straightforward one. If you multiply two negative numbers, which is the first part, then your answer is a positive value. Or you can say then the product is positive, then the answer is positive, then the result is positive. All those would work. Now on the next one, students who use the study guide do well on the tests. It doesn't have an is statement there. So you have to kind of think about cause and effect. So what's the cause here? Well, the cause is students use the study guide. What's the effect? They do well on the test. So my condition is if cause then effect. So if students use the study guide, that's the cause, then the effect is they will do well on the test. So again, you're going to use much of the same language, but you don't have to use the words verbatim. So I switched around the wording a little bit just to make the statement make sense. So instead of saying do well in the test, I said they will do well in the test. That's perfectly fine. You want to keep the core of the sentence there. So the cause is students use a study guide, which is what I did there, and the effect is they did well in the test, which is what I put for the then. So again, the trick here is to use the word is to split up your two statements, or to use the cause and effect sort of outline to guide yourself on which statements are going to fit where. Now the next one deals with different versions of the conditional: inverse, converse, contrapositive, and biconditional. So let's take a look at this. Now it says it wants the truth value, which is just if something is true or false. So let's figure out if this first statement is true or false, because that will help us figure out the other ones. So if two angles are complementary, then their sum is 90. Well, that is true. That's the definition of complementary angles. They have to add to 90 in order to be complementary. So this is by definition true because it's just restating the definition of complementary angles, which is the fact that two angles add together to make 90. Now the inverse is the not version of this. So think inverse is not. So it's not the flipped, that's the converse. The inverse is the not version of it. It's the negation of it. So inverse and negation kind of go hand in hand here. So instead of saying if two angles are complementary, we're going to say if two angles are not complementary, then their sum is not 90. So again, inverse is the not version of it. So all we do is to take the same exact sentence and slip in some nots in there, and then we're done. Now, let's talk about the truth value. So if they are not complementary, then they do not add a 90. Well, if this was false, I'd have to think of a counterexample to prove that it's false. So are there examples of angles who are complementary but don't add to 90? Well, no, because in order to be complementary, you have to add a 90. That's the rule. That's the definition. So this is also a true statement, because if they're not complementary, that would mean they don't add a 90. Otherwise, they would add a 90. So definitions are usually usually true no matter how you flip them around. So if you know that the statement I'm going to give you or that your teacher's going to give you is a definition, like it's just restating the definition in a conditional way, they're probably all going to be true for the most part. Not every time, but most of the time. And in this case, it is true. Now the converse is the flipped. So if you remember when we did this at the beginning, we said that this if part was our P and this then part was our Q. So this went if P then Q. The converse goes if Q then P. So the converse is the flipped version, not the shoe, but the converse is the flipped version. So I'm going to take my statement and flip it. So instead of saying if two angles are complementary, I'm going to say if two angles add to 90, or to make sure that I have the precise language, I would say if two angles sum to 90, just so I'm using the same wording, then they are complementary. So now I have the result first and the hypothesis second of my original statement. I took the back end, put it in front. I took the front end and put it in back. And then I have to figure out whether this is true or false. So if two angles add to 90, then they are complementary. Well, yeah, again, that's the definitions. That's true. That's how we define complementary angles. So this is also a true statement. And as I told you before, inverse and converse always share the same truth value. So if the inverse is true, the converse has to be true. The two verses are always linked together in their truthfulness. And the conditional, which is the starting one, so this one, has the same truth value as the contrapositive and vice versa. So we already know the contrapositive is true because the original statement was. So if your original statement is true, the contrapositive is true. If your verse statement is true, the other verse statement is true. Now for the contrapositive, that is basically a combination of the inverse and the converse. It's the inverse flipped, or it's the converse with knots. I usually think it's easier to say it's the negation of the converse. It's the converse with knots in it. So you can use that to kind of help guide your contrapositive. So we'll say, instead of saying if two angles sum to 90, we'll say if two angles do not sum to 90, then they are not complementary. So again, it's just the converse with the knots in it, or you can think about it as the inverse flipped. So if you flip the inverse, you get the contrapositive. And again, we already said it's true because our original statement was true. Now the biconditional, The biconditional is the fusion of the converse and the conditional. So the biconditional is taking the converse and saying, if this stuff here and this stuff here. So if two angles are complementary, then they sum to 90, and if two angles sum to 90, then they are complementary. That would be the long version of the biconditional. You take your conditional, then take the word and then write your converse. So you have two if-thens linked together with the word and. It's a compound statement. But the shorthand version of it is to simply look at your conditional, drop the if, and replace the then with an if and only if. So let me show you that here. I'll write out the original statement too, so I'm going to keep scrolling up. If two angles are complementary, then they sum to 90. So this is the conditional. Oops, let me get that. Conditional. So that's what we started with. Let me shorten the font here so that I can get it all in one line. So that's what we start with. Though the biconditional, is the same thing as the conditional, but with the if dropped and the then replaced with if and only if. So I'm going to drop the if and replace the then with the if and only if. Oops, only if. So the biconditional would look like this. Two angles are complementary if, well, I should need a comma, if and only if they sum to 90. And that should be a two angles there, not TO, TW. So again, this is the biconditional is simply the original statement, which is this here, but you drop the if, you scratch the then, and you replace it with an if and only if. And the biconditional is true if both the converse and the inverse are true. So if this thing here, my original statement and my converse are both true, then my biconditional is true. And in this case, my converse is true and my conditional is true. Therefore, my biconditional also has to be true. So these are all truth, which is usually what happens with definitions. If you have a definition, they're usually all true, just because definitions are usually reversible, at least for the basic ones. So again, just remember that inverse is not, converse is flipped, contrapositive is both. And then the biconditional is the if and only if. So the next one asks us to use some conclusions using law of detachment or law of syllogism, or we can say law of transitivity if you want the easier version to say. So let's see what happens here in number 9. If two lines are parallel, then they do not intersect. So if two lines are parallel are P, that's our if, then they do not intersect Q. So this gives us lines X and Y intersect. So this is what we have to use to deduce something from this. So we know that if we have P, then we can go to Q. That's about it, actually. So this says lines X and Y intersect. So they give us not Q. Remember, squiggly means not. So they give us not Q, which means we can't really deduce anything because they don't give us our P. In order to deduce something, we'd have to be given the P statement first, not the Q statement. And they don't even give us the Q statement. They give us the opposite of the Q statement. So they don't really give us much to work with. In fact, they don't give us anything to work with because they don't give us P. So the conclusion in this case would be no conclusion, because you don't have a setup where you can deduce this from. If they said lines X and Y are parallel, then we can conclude they do not intersect, and the law would be law of detachment. But because they don't give us the hypothesis, we have to do no conclusion. Now, if you're a little bit intuitive, you could try to be smart about it and do a little bit of investigating here. Because the contrapositive and the conditional always has to be true, if this is true, which we do assume is true, then we can also assume that not Q leads to not P. Because again, the conditional, the first statement, and its contrapositive are always the same truth value. So if this one's true, then this one has to be true. So you could say that the conclusion is lines X and Y are not parallel. And the law of that, you could kind of stretch and say it's the law of detachment. That would be another valid answer for this specific case. That usually doesn't happen, but for those of you that were wondering, yes, you could say that not Q leads to not P. Therefore, the conclusion could be they are not parallel, and the law could be law of detachment that way. It's a little bit of a stretch there, but it would be a valid logical deduction. But for the most part, if you don't have your P and you have something else down here, then your conclusion is no conclusion. So number 10 says, if it is rainy, then the street will be wet. If the street is wet, then driving will be dangerous. Let's give myself some space here. So this is when we have two if statements. So you have two if statements. We want to look to see, is there a transitivity here that we could use? So if it is rainy, that's our P. Then the street will be wet. That's our Q. If the street is wet, well, again, street wet, so that's Q. Then driving will be dangerous. That's R. So Q, then R. So we have P leads to Q. We have Q leads to R. And therefore, we can cut out the middleman and say that P leads to R. So any one of these three conclusions is valid. So our conclusion then would be this one right here. Because if we said this or this, that'd just be restating a statement they already give us. So that wouldn't really be drawing a conclusion. That'd just be stating what they already said. So we want to actually get the one that's a little bit harder to deduce, which is the transitive one. And we can conclude that if it is rainy, then driving will be dangerous. Oops. Dangerous. So that would be our conclusion in this case. Again, we just cut out the middleman, cut out the Q, and have the first of the beginning statement and the last of the second statement. And this law is by law of syllogism, or if you say transitivity, then that would also be true. I know transitivity is spelled wrong because it needs an N in it, but there's a reason I'm not an English teacher. So this would be, again, if you have two if statements, that's your clue that there has to be a law of transitivity or a law of syllogism. If this was not Q, if this was something else, like if it said, if it is rainy, then driving will be dangerous, or if it says, if driving is dangerous, then the street will be wet, or something like that, then we couldn't do anything. So it has to be that this statement here and this statement here have to be the same in order for this law to work. If that's not true, then there is no link, and we can't draw that conclusion from it. So, one more before we get to the proofs here. So, deductive reasoning, as we said before, is based on rules or logic, or you can say facts, reasons, anything like that. And inductive reasoning is based on examples, specifically past examples, so we'll just say examples here. So inductive reasoning is based on seeing something happen over and over and over and over and over and over and over again, and assuming it's going to stay that way. Deductive reasoning is based on rules, logic, and definitions and reason that you know is true, and you can come to the conclusion that way. So now we get to the proof section. So there's an algebraic proof first, and then a few fill-in proofs, and then the last one is a from-scratch proof. So let's do the algebraic one first. So, as with every proof, we always start with our given statement. So let's read our given. 2x plus 5 times x minus 6 equals 4x plus 12. And our reason is that it's given. Always start with your given. So now what's the first thing we have to do? Well, most of you know how to solve an equation. You would start by multiplying this 5 to both numbers. And so you would get 2x plus 5x minus 30 equals 4x plus 12. And we have to give a reason for that, and we know that that's called the distributive property. Excuse me. So that's the distributive property, because we're distributing the 5 to both of them. And then what do we do? Well, for me, I would combine my like terms. So I would do that, and I would get 7x minus 30 equals 4x plus 12. And the reasoning for that would be just simply simplify. If you want to say combining like terms as your reason, that'd be fine too. Excuse me, got something stuck in my throat. But Simplifying is also a perfectly valid reason to write down too. So simplify or combine like terms both mean the same thing. And then for me, next, I would probably subtract 4x. Not the only way you could go about it, but that'd be the way I would do it. So I'll subtract 4x. And so I would get 3x minus 30 equals 12. And that would be by the subtraction POE. So subtraction POE. And then I would probably add 30 to both sides. So add 30 here, add 30 there. And we could probably tell it's going to be the addition POE. So we get, let me send this a little bit, 3x equals 42 by the addition POE. And then last but not least, I would divide by 3 on both sides. So divide by 3, divide by 3. And I would end up getting x is equal to 14. And that would be by the division POE. Remember, POE just means property of equality. So, send that a little bit. So that's an algebraic proof. We usually didn't have much trouble with those. Again, most of you can solve an equation, so it's just solving the equation and then writing out the reasons. If doing it back and forth kind of gets to you, I would just solve the equation like you normally do, and then go back and fill in your reasons after you're done solving it. That might be better for some of you, that way you don't have to keep bouncing back and forth between statement and reason. Just make sure you give a clear line or a clear break when you do each step, so it doesn't get muddled together. So now we get to the fill-in proofs. These are more geometric in nature, but all we have to do first is just fill in the reasons for each statement. And the first reason is almost always our given. So our second statement, let me do this just in case it goes out of whack. They say CD is equal to DE. CD is equal to DE. Well, that would be by definition of a midpoint, because it tells us that D is the midpoint of CE, so D is in the center right there. And if D is the midpoint, that means, by definition, it cuts it in half. Therefore, the first half, CD, has to be equal to the last half, DE. This would be by definition of midpoint. Now, technically, they should have done congruency rather than equality. But again, that's usually a step that some people will gloss over just because it's not that important, I guess you'd say. But in this case, yes, if you're splitting something in half and saying the first half is equal to the second half, it would be by definition of a midpoint. And then the one down here, whoops, get that up. Says CD plus DE is equal to DE plus DE. Now this one's not as easy to see at first, but look what they did here. They took this equation and they simply added DE to both sides. So they added DE there, and they added DE there. So that's an algebra property. So this is basically, not basically, but this is addition property of equality. Because they added the same thing to both sides of the equation. It was just a segment, but they added the same thing to both sides. It would not be segment addition because you're not adding two segments to get one other big segment. You're simply taking the equation you already have and doing the same thing to both sides. So it's slightly different than segment addition because it's not adding two segments to get a bigger one. It's just adding the same segment to both sides. And then this one down here is, again, simplifying. They're combining like terms. So DE plus DE is 2DE. That is just simplifying. And then here, this is where we get segment addition. So this is where they say CD plus DE is equal to CE. And that is segment addition postulate. So that is the segment addition postulate. Because you're adding two segments to get a bigger one. Now here they say 2DE is equal to CE. And again, this might be hard to see, but what they did is they said, okay, since CE is equal to this bit, I can take CE and replace it for that bit up here. I can replace these two statements since I have an equality here. So this is a reason by either substitution, or you can say transitivity. Either one. Substitution or transitive, because you do have your three sets of equalities here. So again, they replaced this CD plus DE. They replaced this statement here with CE, because again, it's both the same. So if these two things are the same, that means I can swap out something of equal value. And then to finish it up, they did the division POE, because they divided both sides by 2. So in case you can't see that, they divided this by 2. They divided this by 2. And instead of saying CE over 2, instead of saying that, they just said 1/2 times CE, which is the same thing. If you divide something in half, it's the same thing as multiplying it by a half. If you don't believe me, use your inductive reasoning and check out some numbers. 10 divided by 2, 10 times a half. 6 divided by 2, 6 times a half, same thing. So this is the division POE for that step. So again, the substitution one was probably the hardest one to see, in addition to the addition POE, because you might have thought it was a segment addition. But again, it's just practice and making sure you take your time and picking apart each little detail there. Now 14 is an angle 1, but it's a little bit shorter, so not too bad. Now in this case, they actually have two givens split up throughout the problem. So the first one says Km bisects JKN. Well, that's clearly a given statement. And then also down here, they say Kn bisects MKL. Well, that's also a given statement. So instead of doing it all at once, they split up their given, which is a perfectly reasonable thing to do. I usually prefer to write all my givens first, that way I don't have to mess with them. But this is a valid way of doing it. And the reason they did this is to probably make the second and fourth statements a little bit clearer. So they said that JKM, so JKM, this angle right here, is equal to MKN, so which is this angle right here. And how can we tell that those are equal? How can we tell that those are congruent? So if I draw a congruency thing there, how can we tell that those two angles are congruent? Well, that's by the definition of a bisector. Much like a midpoint up here, the midpoint cut this segment in half. Down here, the bisector cut this angle in half. So you have half the angle on this side, which is JKM, and half the angle on this side, which is MKN. So this is by, just like definition of midpoint, this would be by definition of bisector. Bisector. There you go. And you can probably tell that this is the same reasoning too. So if I go back here, MKN, which again we said this green one here, is congruent to NKL, which is this blue one here. So it's saying that these are also congruent. This one and this one are congruent. And once again, that has to do with the fact that we have a bisector there. So this is also just definition of bisector. Because once again, just like a midpoint splits a segment in half, a bisector splits an angle in half. And you can probably tell by now that we have congruent, we have congruent, we have congruent. So we have three sets of congruencies. Therefore, we're probably going to have to use substitution or transitive property. Transitive. And if you can't see the substitution, I'll point out to you here. So we have MKN here, and we have MKN here. So if these are equal to each other, that means this thing has to be congruent to that thing. Because again, I'm just cutting out the middleman. Just like P, Q, Q, R, cut out the middleman and you're left with PR. Just like you would with statements, except we're doing it with reasons here. So this entire quiz is mainly the same thing applied to three different cases. One with statements, one with segments, and one with angles. But it's all a matter of, basically the big ones there are midpoint, bisector, substitution. And then of course definition of congruence when it pops up. And then the last one is our from scratch proof. So this one we have to do by ourselves from nothing, which is fine. We can do that. So let's see if I can't get this written in the same amount of blanks that I gave myself here. So we start with our given, right? So instead of writing our given, I'm just going to put some placeholder here. So, because I can't really do, actually, let me try it. Let's see how clean my handwriting is here. So we'll say AB is congruent to CD and BE is congruent to DE. And this reason is by given. That's not too bad. So AB congruent to CD, BE congruent to DE by given. So now my goal is to get AE. My goal is to get this big segment congruent to this big segment. So before you even start writing, think to yourself, okay, I'm looking for two big segments to be congruent, AE and CE. Those are my two big segments. So I'm probably going to have to break them down first, because the way I prove segments congruent is I prove that their pieces are congruent, and then I can say the entire segment itself are congruent. So I first need the pieces. In order to get the pieces, I need to use segment addition. In order to get the segment addition, I need to use equality, not congruency. So my first step is to probably go back to equality. So I'll say AB equals CD and BE equals DE. That's a B. And this is by definition of congruence. Again, you can write the symbol rather than the word if you want to. So now I have an equality, and then as I said, if I want AE, if I want this, I probably want to talk about its pieces here and here. I want to show it broken up into pieces. So I'm going to go ahead and write that. I'm going to say AB, or sorry, rather AE. AE is equal to AB plus BE. So I'm saying that the big segment is made up of these two small segments. And then I'm also going to do the same thing over here. CD and DE make up my big segment of CE. That makes up that big segment. So I'm going to try to squeeze that in here the best I can. So I can say CE is equal to CD plus DE. And this is where I use my segment addition postulate. Because I'm taking two small segments and adding them together to get a bigger segment. Now I need to find a way to link this, because again, my goal is to link up AE with CE. I want to get them congruent. I want to get them together. So I need to think about, can I replace something in their sums so I can get this sum equal to this sum? A little bit of a scratch there. Now, I can also go backwards. I can try to get CE to equal AE, but let's stick with one at a time. So let's see if I can't try to get this here to be equal to that there. Is there some substitutions I can play with? So I'm going to write AE equals. So is there something I can replace AB with that would get me closer or to here? Well, yeah, right here. It says AB equals CD. So that means I can take this AB and replace it with CD. And then what about BE? Is there something I can do with that? Well, right here, it says BE is equal to DE, which is what I want. So I'll go ahead and replace that. BE with DE. And the reasoning for this is by substitution. And you have to forgive any misspellings. Or by, in this case, it wouldn't be by transitive because there's not three sets of equalities. But if you said transitive, you're not too far off. But in this case, it's substitution because you're taking one segment and replacing it with one other segment. So it's a little bit more of a direct thing than transitive would be. And now if you look at it, we have CE is equal to this thing, and you have AE is also equal to the same thing. We have a link here. There's a bridge, there's a link, there's a road, whatever you want to call it. But there's a link between these two segments, which means that I can say that the segments themselves, AE, is equal, not congruent yet, to CE. And that is also by substitution. So remember, you can use the ditto marks to say the same thing as above it. This just means take the reason above it. So now that I've built my bridge and I've crossed it, I've said CE is going to travel this bridge and become linked to AE, which is what I want, but I want them to congruent, not equals. So I'm going to finish it off by saying AE is congruent to CE. And that would be by definition of congruency. And again, if you notice here, our first two steps are usually always the same, and our last step is usually always the same. By definition congruence, and of course given at first. And then usually segment addition postulate usually comes in around the third or fourth step. And then usually between segment addition postulate and definition of congruence, there's usually substitution or transitivity going on in these steps. Sometimes maybe an addition POE here or there, but usually substitution or transitivity. So not every proof is the same, but they follow certain guidelines. Given first, then for us, at least at this point, definition of congruence. Then once we get into definition of congruence, we're back to equality. So we can use the segment addition postulate to set up some sums. And then we usually use some substitutions twice or 3 times, depending on how big the proof is, to switch things around so that we can get our equality that we want. And then once we get the equality we want, we change it to congruency with definition of congruence to finish it out. So again, these proofs kind of be exhausting at first, but again, with practice and with time, they become a little bit more manageable. So that's it for this study guide. Hope you enjoyed the video. Good luck on your test. Have a good day.